tap your card. In that instant, an invisible global border checkpoint has exactly 300 milliseconds to decide if you are the legitimate buyer or a fraudster. This diagram shows the sheer scale of the queue. Visa alone handles over 233 billion transactions a year. Their network can carry up to 65,000 messages every single second. This scale is a planetary requirement. In Brazil, the Pix network clears 178 million transactions in a single day. India's UPI system handles over 12 billion transfers a month. On a multi-trillion-dollar river of commerce, even a microscopic fraction of fraud adds up rapidly. Global card fraud drives over $33 billion in losses annually. Human oversight is impossible at this velocity. AI is the only entity capable of manning this global gate, acting as an instant interrogator for billions of people. The core mathematical problem of fraud detection is imbalance. Actual fraud represents a microscopic fraction of all transactions, roughly 0.172%. It is a literal needle in a moving haystack. This animation shows why standard accuracy is a deceptive metric here. A model that approves 100% of transactions and catches zero fraud is technically 99.8% accurate and completely useless. Older security systems relied on handwritten if-then rules, but those rigid checklists break down against adversaries who mutate their tactics the very minute a rule catches them. Defending a moving border requires dynamic judgment. The system has to evolve from asking, "Does this break a known rule?" to asking, "Does this look like you?" To see how that judgment works, we have to slow down the clock. We are going to look inside the strict 300 millisecond budget of a single payment decision. This flowchart shows the real-time scoring pipeline. The critical engine is the feature store, rebuilding historical context and fetching data points in under 10 milliseconds. One primary metric is velocity, flagging anomaly clusters like 3 credit cards used in 3 minutes from one device. It runs a geospatial impossibility check. The AI flags anomalies, like buying gas in Texas, then attempting to buy a watch in Singapore 5 minutes later. Machine learning models instantly ingest over 1,000 of these signals simultaneously to render a final risk score. The AI achieves this speed because it isn't relying on human intuition. It is instantly calculating the mathematical distance between this single transaction and your established digital identity. This diagram shows how fraud hides in plain sight. In isolation, a single fraudulent transaction looks perfectly innocent, but graph neural networks score the entire network simultaneously. Tracing shared attributes, the AI spots the ring, seeing dozens of cards routing through a single device. At the real-world scale, payment networks like Alipay use these graph networks to map 1 billion users, taking down entire criminal rings preemptively. Criminals can spoof an identity or an IP address, but they cannot easily hide the vast structural geometry of their entire web of connections. The attackers are also deploying artificial intelligence. In one recent case, a company wired $25.6 million after a video call where the executive requesting the funds was a completely AI-generated deepfake. This creates adversarial drift. Fraudsters constantly rotate their tactics and proxies to evade detection, causing the AI model's accuracy to silently decay over time as its old rules become obsolete. And the defenders are caught in the delayed label trap. If an AI successfully blocks a transaction, it never gets proof of whether it was actually fraud, leaving the model blind to its own performance. To counter this, companies have to do something counterintuitive. They purposefully let a tiny, random holdout of high-risk transactions slip through. They pay the cost of about 1% of suspected fraud just to observe the truth and retrain the model. This is an endless arms race, where the system must constantly retrain because the enemy learns from every blocked attempt. This animated loop illustrates the ultimate collateral damage of the cycle. Wrongly turning away legitimate customers at the checkout costs the economy over $150 billion, which is more than the actual fraud itself. Because algorithms can accidentally learn demographic biases, laws like the U.S. Equal Credit Opportunity Act and the EU AI Act make black box decisions illegal. The AI must be able to mathematically explain its exact reason for every rejection. This real-time engine scores billions of actions to decide if you are allowed to proceed. But what happens when this exact same architecture is pointed at predicting what billions of people want to see next?